open my Jupyter notebook in the quantum experience, I'm gonna zoom my screen here. Let's see if I can do it without jeopardizing the view. I believe this might be good enough. Is it okay? So, yeah. If you guys followed last week, I can show it again with no problem. The way you upload your homework to the quantum experience is, of course, you open your quantum experience. Your computer by this time should have an account. Then what you're gonna do, you go into Canvas. I'm gonna open my Canvas here. You go to Canvas. You go to the course. You go to the modules. And you will find the homework in week 17. And then you find the not the lab 17, the homework 17, sorry. Homework 17 is here. So you're gonna download it. Once you download it, you go to a quantum experience, you go upload file. Then you go to your computer, you find wherever you saved it and you download it. So I have mine already here. And because I've done it before, mine is already like written, but I'm gonna redo it with you guys. So yeah, let's get started. So I'm gonna read it aloud with you guys because when we read it, we understand better. So first thing we have to do here in this notebook is making it run. So Shift Enter should make it run. And it's important because in the first module here, in the first cell, you have everything imported as you need to make your program run. Okay, so importing Qiskit as Q, NumPy as NP, and Matplotlib .pyplot as PLT. This will make, when you import them as shorts, it makes it easier to make them run. So yeah, I run this already. So let's see. The activity 1 is solving tensor product by hand. Tensor products allow us to describe systems of multiple subsystems. That means that it allows us to describe a 2-qubit system in terms of the individual qubits. So there's a link to a page that explains better what's a tensor product, but I'm going to show you guys how to do it. First, we are going to solve some things by hand. It's important that we practice by hand so in the future you understand what you're doing to not get lost. It's a simple operation, but we're going to do it by hand, so we're going to see it now. So first thing is we're going to write the state psi, which is given by 0, 1 times 1, 0. 0, 1 tensor product, which is not an ordinary product. 0, 1, 1, 0. So tensor products are solved in a different way of an ordinary product. And the way you do that, you're going to first, I'm going to do here because we have more room here. I'm going to copy with more room here, 0 and 1, which is our first vector. And I'm going to repeat this vector here. For each element of the first vector, I'm going to repeat this entire vector. And that's how we do it. Oops, yeah, correct. So This means you're multiplying this constant by the entire vector here and this constant by the entire vector here. As a result, because you have two vectors that have two lines in one row, we're going to have a vector that's one row, because it's a vector, with four lines. And the result's going to be 0, because 0 times 1 is 0. 0 times 0 is 0. 1 times 1 is 1. 1 times 0 is 0. Oops, yeah, correct. This is going to be the result. So the first activity here in our notebook is asking us to write the result of this operation, which is 0, 0, 1, 0, in a way Python can read it. So I've already written it here, but I'm gonna delete it from here, and we're going to write it again. Okay, so let's do it. We have vector psi, vector psi. It's gonna be NP array because that's how Python understands our vector. We're gonna put the square parenthesis and another square parenthesis, and we're gonna write each element of this vector in here. That's how Python is gonna read it. I'm sorry, it's 0. Third element is gonna be 1. Last element is gonna be 0. I'm sorry. And we need to either call this variable, or if you want to get rid of the word array, you just print the variable. You can also do that. Okay. So if you just want to see the vector, you don't need to print it, but if you want to see it nicely, you print it. It's up to you. Okay. So that's how we write the vector. So next question. We now are required to multiply this matrix by the state we got in the first question. Okay, that's how we're gonna do it. We have the end state is gonna be called phi. We have this matrix here. And erase the excess. And okay, so if you guys look here, this matrix, if you isolate portions of this matrix, you see it's a 2x2 identity matrix here. And this is a very known gate for us. It's the X gate or the X polymatrix. It's the X matrix. So it's the X gate, and all this together is a C0 gate. We're gonna see again. And our psi vector was 0, 0, 1, 0. And what we get from that, it's gonna be a vector, because when you have 4x4 matrix multiplying a 4 by 1 vector, we see that these indexes here coincide. So it's feasible operation. The result is gonna be a 4 rows, 1 column thing. It's a vector. Vector is 1 column with 4 lines. So let's see. How do we perform this operation? We're gonna have this entire line multiplied by this column. We go item by item. You're going to multiply 0, 1 by 0. Then you're going to add 0 multiplied by 0. Then you're going to add 0 multiplied by 1, 0 multiplied by 0. So this is going to be 0. And then if we keep going, we're going to see that the vector we get in the end, because every line here is going to be 0, but this last one, 0 times 0 is 0, 0 times 0 is 0, but 1 times 1 is 1. So this is the result, and this is the vector we should be writing here. So here we need to write this vector, and because I did it before, it's already written here, but I'm going to write it again. Oops, not here, sorry. Here, the result of the multiplication. So we're gonna write, just simply write the result. We're gonna, here we have a hint already how to do that. If you look here, you already know how to do it, but we're gonna write it again step by step so you don't get confused. Just in the same way we did for the other vector psi. And now we need to see the vector. And if you don't want to see, the word array here, we just print it. Here's our vector. So 0, 0, 0, 1 here, in a way Python can understand. Okay. Okay. So here we created a 2-qubit state and applied our state to a 2-qubit gauge. What were the initial states and what were the ending states? What kind of gate is shown above? The gate I just, because I'm gonna answer backwards this question. When you look to this matrix, what you see that a portion of this matrix is an identity matrix. This is 0, it does nothing. This is 0, it does nothing. And a portion of this matrix is the X matrix that flips the state. It's a kind of inverted identity matrix that flips the state. And this is called C0 or C0 gauge. That's the matrix, that's the mathematics of what we do when we apply a C0 to our circuit. And what were the initial states? What were the initial states? Let me show. So the first vector we had, as we know, zero, zero, 1, 0, yeah. And this was the result. The psi vector was the result of 0, 1 and 1, 0. 0, 1. You see, it was 0, 1, 1, 0. So these, I'm sorry, I did it wrong. I'm super sorry about confusing you. It's my mistake. Super sorry. This is 0, 1, 1, 0. It's this state here.
Gisele, this is part of doing quantum computing, right?
Yeah.
Don't apologize. Part of the process.
Yeah. Sometimes I get confused myself. So, but as a student, I used to get mad at my teachers for committing mistakes. Now, when I teach, I see how hard it is. So it's a huge responsibility. So this is our initial state, okay? And it's 1 and 0. And when you do this product, 0, 1, 1, 0, that's what it means, okay? And it means I had a circuit, initial circuit. Initial circuit like this before. When my Q1 was 1, my Q0 was 0. And then we applied a C naught here, where the target was Q0, and Q1 was 1, was the control. And how we know that? Because the resulting state had 1 in the end. So we know we flipped this in the end. This became Q0 became 1, 1. And that's this state here we saw on the last homework section. Let's see if I'm not saying anything wrong. I'm going to do the tensor product here again. And when I sort this out, I see it's 0, 0, 0, and 1. And that's the final state here. And that's how we process to think this bonus question too. So if you see, it's not hard. It's simple calculation. It's always simple numbers. But if you write one number wrong out of order, you get it all wrong. You can get confused. So I challenge you guys to look at this and to try to do by yourselves and to think and reason and try to get to the same conclusion. Do your own calculations and try to get to your own conclusions. Because if you don't practice this, things get much more confusing. So it's very important to have a solid basis. So it's a bonus question, yes, but it's very important to think about it and understand how it goes, how it works, and try to do by yourself. Do many times this type of calculation here, try different numbers. Whenever you see a big matrix, don't get scared of it, try. It's true that like when it gets much bigger than 4x4, it's gonna be a bit harder. So try with 4x4 matrices and try to do by yourselves. But it's important to get a very solid basis, because it's gonna get more confusing if you do not understand it now. Okay, it's not hard, it's simple. You guys did great so far, because if you're following this far, it's because you are interested. It's a great thing, but try by yourselves, okay?
Sorry, can I ask you a question
Yeah,
here?
of course.
In
Of course.
in previous slide, yes. How did you know that this initial psi number is 10?
I'm gonna show you again.
Okay, thank you.
Do it again. I'm gonna show you. I know it's this because the homework told me it is. To see here the size stage.
Yes.
So this 0, 1 means vector vector 1.
1, yes.
Yes. And 1, 0 means,
Oh, yes, you represent it by qubits. 1,
yeah,
0.
yeah.
And together. Okay, then thank you. It's
This
clear
is
now.
yeah, cool. This
Thank
is
you.
called the bracket notation. This is the
Mhm.
cat. We call it cat 1, cat 0. And these are two ways of representing it. Okay?
Great,
It,
thank you.
okay. Welcome. So yeah, cool. By the way, the lab this week was super cool. They talk about that. So if you guys can go back to the recording of the lab and see it again, the instructors went through that. They were great. It was a great lab this week. Explained very well. So at least the instructor I had explained it very well. I hope you guys can follow it because they say about it. So it's never too much to keep reinforcing this learning. Okay, so we already did the bonus question. So now we are in activity 2, that's solving the tensor product using NumPy, which is great because now we don't need to do any calculations, though I strongly advise you to practice. Now we have a way to check if our calculation is correct using Python. So let's read it together to make sure we understand everything, okay? Now that we've got the hang of doing things by hand, let's do it in Python. To perform the tensor product of A and B in Python, we use np.cron AB. Cron is short for the Kronecker product. And advanced math notation aside, they will do the same matrix operation that we need. So mathematicians call it Kronecker product, okay? That's why it's not tensor here, it's cron, but it will work very well for us. If you guys have any doubt, I recommend later to check the documentation because it's always helpful, okay? Since we have Python to do the heavy lifting, let's do what we did earlier, but generalize to more qubits. QxQ uses right indexing. Part of Qiskit's internal structure means that bit strings are always right indexed. That means, as I explained it in here, like Q0, Q1 in this order. Qiskit does the same, does Q0, Q1, Q2, Q3 from right to left, okay? It's very important to remember that to understand the logic that follows. Is representing the state qubit 0 to qubit 3 from right to left. Example, 0010 means qubit 1 has been flipped. Yeah, we will see more like further. There are more examples here. So using np-cron, print the matrix representing the following. Yeah, so it's gonna be every vector is a matrix, not every matrix is a vector. A vector is a matrix with only one column. That's why it says print the matrix, okay? So let's see here. The psi vector they want here is a sequence of tensor products. Tensor product is not commutative, which means you cannot change the order of the vectors you're multiplying, but it is associative, which means like you associate, you can put the parentheses here and you can put the parentheses here. You can do the parentheses here. So it doesn't matter where you put your parentheses because it's associative, okay? So what I'm gonna do here, I'm gonna write the vectors I already did in the same sense we did here in the first questions, but it's already written here. So I can just write one of them again just to show. So vector A, I'm calling this one. Vector B, I'm calling this one. C and D, okay? So vector B, vector A, sorry, it's gonna be np.array. And pay attention because sometimes I myself commit this mistake. I forget an R here. It's very important to type it correctly because you're gonna see an error message, and if you have a big code, you're never gonna find your mistake. So be patient and go slowly when you're typing. Okay, it's gonna be 1 0. So I'm gonna write 1 in the first box. I'm opening the second box into 0. It's gonna be my vector A. And if everything is correct, now I can write the chronicle product. And what I'm gonna do, I told you guys that it's possible to put the parentheses here, and it's possible to do the parentheses here as well, or in the middle. The way I'm gonna do here, and then here, as I'm putting the parentheses here. So I got another variable called E, just because it's the next letter. It doesn't matter the name you do, as soon as you consistent what you naming your variables. I'm gonna call the chronicle product doing np.chron, and AB are gonna be these first vectors here. Okay, so I'm gonna have a new variable that's gonna be the product. And I'm gonna call another variable F that's gonna be the product of C and D, as I'm putting the parentheses here. And what I'm gonna do in the end, I'm gonna call psi the chronicle product of E, that's the first parenthesis, and F, the second parenthesis. And then if I press Shift Enter, should see my result. Yeah, of course, I'm printing the variable. Okay, you have to call the variable, otherwise, if I don't print the variable, I can't see it. It doesn't give you any error message, but I also don't see anything. So it's important to call your variable if you want to see the results. Okay. Sometimes you're writing a big piece of code, you don't need to see the result. So, okay, you don't print it. But in our case, we want to see the result. So that's why I'm calling the variable here. So another way to do this, I'm gonna mute this for Python. Whenever you put the hash symbol there, you mute it. For Python, it doesn't read. I'm gonna delete the hash symbol here just to show you guys this. If I want to do it differently, I'm gonna mute these variables too. What I can do is writing directly here. It's exactly the same thing because in this case, I have explicitly written E here and explicitly written the F variable here. And it works exactly the same. It gives you exactly the same result, okay? So it doesn't matter how you perform since you keep this order going. Okay, it's important to not change the order of the operations you're doing. It's not the same putting this vector in front of everything. You're gonna get a different result. But if you follow the order, it has associative property. Okay, so to not.
So I have a question here.
Yeah.
So the cron here is a tensor product in Python, is that right?
Yeah.
So do you need to import any package to use the cron?
Can you say again, please? I didn't hear you very well.
So do you need to import any package to use the cron, or by default you don't need to import anything and you can use cron?
Now it's here. It's the NumPy. It's imported here. NumPy has it.
Oh, okay, you will have to do it in NumPy. Okay, thank you.
Yeah, it's NumPy. So the hint that is NumPy, it's because it's, I'm gonna show you the chronicle product here. You have np dot, so that's NumPy.
Okay, thank you.
Welcome. So yeah, it's another hint. Sometimes your things are not running, your cells are not running. It's just because sometimes you forget to import the things here. So it's very important to remember to import them correctly. Yeah.
Hi, what's the proper way of describing the psi matrix? Make sure I'm reading it right. How do you construct the matrix out of that from your pi result?
Oh, yeah. The thing is, it's calling it a matrix because every vector is a matrix, but not every matrix is a vector, because a vector is a special type of matrix with only one column. Is that your question?
Not quite. I was wondering, what does the psi matrix look like mathematically when you guys when you actually create the matrix, when you actually write it out? What does it look like? What does the phi result look like? Is it 4x4?
No, it's gonna be a 4x1. It's gonna be this. That's the matrix you have. It's this. If you like, I can write it for you now, because it's part of the process of learning and understanding. Okay, I'm gonna write it for you. It's 1 0 1 0 0 1 1 0. Just to not forget. This is it. Psi. It's called matrix, but it's a vector because vector is a special type of matrix. But anyways, let's do it by hand.
Thank you.
Oh, welcome. So I'm gonna do as I did in the Python, where I put the parentheses here and here. So I'm gonna solve these two separately, okay? So we can get a better understanding. So let's solve these first. To solve this, if you guys listen to some shouting, it's my stepdaughters playing video game in the other room, and I'm intentionally saying that because I asked them to be quiet and they're playing it very loudly. So I would say next time I will tell their names if they don't behave.
Giselle, you should force them to come in here and learn this.
Sorry, what?
You should force them to come and learn Qiskit.
Yeah, well,
That's great punishment right there.
next spread, I'm gonna have both sitting here and
Yeah.
teaching you again. Okay, that's gonna be the next thing.
I love it.
Be
Yeah. Say what? So I'm teaching how to do the tensor product, and I'm doing like this first bit here. they defocus me so much that I'm showing it my hand instead of showing it my mouse. But I'm doing this, and then I'm gonna do that. So let's focus on this bit first, okay? I'm doing the tensor product. And the way you do the tensor product, you copy this first vector here, and you reproduce the entire second vector here. So you're gonna do a constant multiplying a vector for each side. So as a result, I have 1 times 1 is 1, 1 times 0 is 0, 0 times 1 is 0, 0 times 0 is 0. This is going to be the result of this first parenthesis, okay? So following, I'm going to copy the first vector here and twice the second vector. So 0 times 1 is 0, 0 times 0 is 0, 1 times 1 is 1, 0 times 0 is 0. Okay, now be prepared for a really big vector, and I hope to not mess up. Let's see. So psi is going to be the result. 1, 0, 0, and 0. Times, I'm going to copy the second vector here. 0, 0, 1, 0. 0, 0, 1, 0. 0, 0, 1, 0, 0, 0, 1, 0. Okay. Let's see if I'm gonna have room to write this. I'll try to write it small to make it fit. So 1 times 0 is 0, 1 times 0 is 0, 1 times 1 is 1, 1 times 0 is 0. And obviously for all the rest, all the other 12 numbers I have here, I'm gonna have 0 because I have zeros multiplying them. So I'm just gonna write a collection of zeros here and very tiny 0 in the end here. But that's the vector. It's a 16 lines vector because I have, whenever I multiply by the tensor product, I double the, it's not correctly said, but like I multiply the number of lines I have because as I repeat it here, it gets a bigger and bigger and bigger vector. So if I start with like 4 vectors with 2, it's like this. It's the power of the number of variables I have and the number of lines I have for each multiplication. Anyways, it's a 16 vector. 16 vector that I have here. Oh, I shouldn't have minimized it, should I? If you see here, it's 16. 16 lines, and that's what I have here, 16 lines, okay? Did I answer your question?
Yes, you did. Thank you.
Oh, cool, welcome. So yeah, as I was telling before, sometimes we can't be lazy. If you want to understand, we need to go hands-on and try. But like knowing that Python works so well, it's a great alternative because we can tool here in Python and just check. It's great. So you can do by hand and then come here and check and try to understand what you're doing if you're doing it correctly. So now, using these matrix definitions of not gate and the identity matrix and the Kronecker product, print the matrix representing the following. And now we know it's going to be a matrix because a Kronecker product of matrices is going to be a matrix. It's not going to be a vector anymore because you know it gets bigger and bigger. So yeah, let's do it. So first step we need to do, I'm going to do just for the identity matrix, just to show, just because it's easy to do. I'm going to show it here and then we're going to do with Python. So the identity matrix 4 by 4 is given by that. So if I want to do Kronecker product with these matrices, following the logics that we learned before, what we're going to have, gonna rewrite this matrix here. And I'm gonna write the second matrix here again. And then let's see what we get. So we're gonna repeat the first matrix because it's 1 times this matrix. So obviously it's gonna be 1, 0, 0, 1, because whenever you have a constant multiplying a matrix, you gonna have this constant multiplying each element on the matrix. So following this logic, we're gonna have a collection of zeros for the next matrix. The same here. and repeat the matrix here. And I hope I'm clear enough. So what we have here, gonna diminish this gap just to make it prettier. Just gonna write it closer here. Yeah. 0, no, sorry. 1, 1, 0, 0. Okay, as a result, that's what we get. Okay, so that's the calculation we're doing here. So what I did, to write a matrix in Python, we don't need to put the np.array. It understands if you write it like that. Parentheses, square parentheses, 1, 0 is the first line, 0, 1. Okay, I'm gonna mute this for Python so I can show you guys what I'm doing. So what I did, I just simply write the I matrix, and I'm gonna call I2 the product, the canonical product of these two matrices. That's this calculation here. And then I'm gonna check I2, and I check. And this is exactly this matrix we got here, showing that my calculation is correct and that Python is doing its job. So now, what we're gonna do, gonna mute this, and then I'm gonna unmute this. I'm gonna write the C0 matrix line by line. So what we do here, we write parentheses, square parentheses, and each line of the matrix is gonna be one little package, I call it little box here. Okay, that's how you write it. And now I already have the I2 written here. So the U matrix is the product of this I called I2 already. So the U matrix is gonna be I2. That's this matrix times C0. And we're gonna call the matrix to see the result. And if it doesn't bug, here we have it. This gigantic matrix, but yeah, that's it. If you look carefully at each part here, you're gonna see you have a collection of identity matrix and X gates repeating on the diagonal. So I like to observe and understand it. I'm not going to do the calculation with this gigantic matrix, but it's interesting to go and check what you can identify here. You can identify a diagonal matrix here. That's the identity matrix. This is the 2 by 2 X gate. So it's interesting to see and observe the behavior of this matrix. Anyways, this is the matrix.
A question: is there any application of this calculation? Why it needs two identity matrices from the very beginning?
Yeah, it's just a way to show you don't need to. It's just showing you how the matrix work, because in reality, when you're writing your quantum circuit, you don't need it. But mathematically, it means that when you apply an identity matrix, you are doing nothing to your qubit, But for completion, to complete this gigantic matrix, you have to have the identity matrix in place. So that's the mathematical artifact you're gonna use to make your matrix work. So when you write your circuit, I'm gonna show down here, you don't need to write the identity matrix, but in reality, in the background, what you're doing, mathematically saying, is that you're using an identity to complete your matrix. I hope I'm clear enough. We're gonna see more, you're gonna understand it better in the next, in the following. I believe you can understand better. If you don't, you ask me again, okay?
Yes, before we move on, can I ask, when you write I identity matrix, does that specify the dimension of an I?
No,
No.
no. Identity matrix is any matrix that has this diagonal as 1. It's sorry, I'm gonna put my
But how
pen.
do you know whether it's 2 by 2 or 4 by 4 identity matrix I?
Here you mean in Python, or you mean like when you're working with stuff?
Well, for example, the one U equals to I TensorFlow I tensor product I, and then so here the I is like a 2 by 2 I or 4 by 4 I. They're all
Yeah. It depends on where you're applying things. If you're applying to a system where you have 4 qubits, you need an identity that's 4 by 4. If you're applying to 2 qubits, then you need an identity that's 2 by 2. It depends on the system you're working on. But identity matrix is any matrix where you have a diagonal with ones, like this one, and all the rest is zeros. Any matrix in this shape that's square matrix, I mean 4 by 4, 5 by 5, 6 by 6, 100 by 100, but the diagonal is made of ones and all the rest is zeros, is called identity matrix, and it's going to be an identity in the system it's performing in the operation. It depends on the dimensions of things you're working with. So depending on the system, you have different dimensions of identities. It's the same for a constant as multiplying by 1, a constant. But constant is dimension 1, so you only have 1 here. Okay, so it depends on the system you're working. It's the equivalent of multiplying a number by 1, you're gonna get the same result. If I multiply 1 by x, I have x as a result, so we call it an identity operation. Okay?
right. Actually, here is like a I tensor product I. Here I, you by default you assume it is a 2 by 2 identity matrix.
Because
Actually,
because
equivalent to a 4 by 4
define here.
identity. Right. But actually, it's equivalent to a 4 by 4 identity matrix by itself.
Yeah, well, here in this case, I am calling it identity matrix. The exercise didn't call it, and Python is not calling it like that. I'm choosing to give the name of matrix I identity because I know it is. So it's different how you define it here in this NumPy, how you define it here. I think TensorFlow defines it differently, but here for NumPy, I could call it another name. I don't need to call it I. I'm just calling I because the exercise asked me to. I know its identity because like I see it is. So I know the dimension because I chose to write like that. So that's how I know the dimension. I know it has 2 lines and 2 columns.
In Python, do you have a like a shortcut, like a function for you to define the identity matrix of a certain dimension? You don't need to define it yourself.
Yeah, but like I'm just following what the exercise asked me to do. So I know it's identity. Because I, I define it here. So I know it's identity. Because I know the dimension. I know its identity. So that's how I know the dimension. is asking. So I'm not saying different because at this moment it's just important to learn how to perform operations with NumPy. But yeah, I'm not going to this now, but like I'm just doing what the exercise, the homework's asking to do just to make it easier. So that's why I'm not doing it now. But yeah, of course, you have other ways to define it. I'm just not doing it now because we just needed to understand the logic of the exercise now. Okay.
Okay,
Thank you. So yeah, so following, I did the C0 matrix, and it's a 4x4. So I write 4 boxes, as I call them, here. And then I'm doing the chronicle product with them. And then I have this matrix, the big matrix, 16 by 16. So now finally, we're gonna use the dot product to apply a matrix to a vector. So the psi vector is our friend psi vector that we found here. We already know it, I already defined, I already have it here. So Jupyter Notebook already has it. So I'm going to use it. So I only need to repeat it here. I'm going to use dot product, and the U matrix I already know because I already defined it here. So it's a very simple operation, just using the dot product as it follows here with U and psi. And then we have our result. So if we apply our 16 by 16 matrix to a 16 vector, 16 row vector, we have this result, this 16 by 1 matrix or vector. Okay. Then, yeah, so now we're gonna see the unitary gate construction. It's missing an S. Now I see it. It's missing an S here, but whatever. We're gonna do a unitary gate.
can you hear?
Has the microphone open? Could you please close it? Yeah, so so let's do it. I can answer more questions in the end, but I'm just trying to keep up with time here. So yeah, we have this introduction here. Let's read it to try to understand better. Now that we have created a custom 4-qubit gate, U-gate, we can pop it into QxQ and simulate. We need to use 2 new things. First, we need to use the quantum operator class q.quantuminfo.operator u. It's given, it's what you're gonna call. So that's not too much to explain here because that's the variable you're gonna, not the variable, that's the operation you're gonna call. And this takes a matrix U, that's the one we defined, but could be another matrix that we would define in a different way, but it happens that we're gonna use matrix U, and makes it a proper operator. Next, we need to make the operator into gate using QC.unitary. And that's the other thing it's given. QC, it's our quantum circuit. Okay. That we're gonna draw and gonna define. And we're gonna use this command. And the label is the name I'm gonna give to it. I'm gonna call it U because that's the name of the matrix we used. But it could be another name, whichever name you would like. It's just a label. And this function takes 3 variables, which is a quantum operator, the string containing all the qubits this gate operates over a label which gives a gate name. In our case, we would like our U gate to operate over all 4 qubits. So we're gonna call all 4 qubits. Okay, so this is the command we're gonna use. We basically gonna copy and paste it here. Okay, so first thing, we need to define our quantum circuit. I'm just gonna call it QC because it's the easy name. So I had already done it here, so I'm not gonna redo it. Did last week. I have it ready here. And I'm gonna call 4 qubits because that's how we define it. That's how the exercise asks us to do. It asks us 4 qubits. So I'm gonna give 4 qubits and no classical bits now. But one of the qubits needs to be a vector 1. So we're going to use the next gauge applied to qubit Q1 to be our 1 vector. And the other ones are going to be zeros by default. And then we're going to draw a circuit. Okay. So I believe this is already, even in the notebook, I don't need to redo it. It's already in the notebook. So, okay, now we're going to use the state vector simulator that we used last week as the back end. We learned this in the last homework. So if you have curiosity, you should. If you didn't do, you go do. Homework 16 has these commands. That's where it came from. We're just gonna check, we're gonna run these commands in the state vector simulator just to check if our state is correct. And it is correct, it's the state 0010, representing this circuit here, okay? Qubit 3 is 0, qubit 2 is 0, qubit 1 is 1, qubit 0 is 0. Okay, so now we're gonna use the operator class that was described before and use our U gate that we defined before as well into the circuit and simulate the state vector. And what we did here is simply we copied the instructions here because the notebook taught us how to do. I simply copied it here and pasted here, just checking that my circuit is actually called QC. And yeah, and I'm just using the operator U that I defined before. We defined this operator U when we defined this matrix here. This is operator U. But this is great because it's already defined here as U. We don't need to write a big matrix anymore. We just need to call U. And that's it. We can draw a circuit. And this U is applied to all of the qubits. And that's why we see that some of the matrices, and when we're producing this U matrix, is identity, because in fact, we're going to see what it does. I'm going to show now. So before doing the next step, we're just going to introduce the QxQ simulator, because so far we use the state vector simulator. And the state vector simulator just show black and white what you expect to see. It's just like, yeah, that's how quantum physics work and that's how it should be. But the QxQ simulator is a simulator that makes our classical computer to work as if it were a quantum computer. So it's a simulator. It's not a quantum computer yet. It's just a simulation, okay? But like introducing some noise, because real quantum computer have noises. It just doesn't give us like exactly the value we expect, but give us a result close enough. So what they're trying to show here, to use the QxQ simulator, we need to add classical bits. So now when we're trying to generate the phi plus Bell state that we saw last week, we're gonna do with calling 2 classic bits to help us to show how the QxQ simulator works. So to generate this, it is already in the notebook, but if you do not understand, go to last week's work and check it out. It's very well explained there. You can see how to generate the circuit. And now the thing we adding is the classical bits, and we are measuring, we adding and measuring here. That's reading from our qubits and sending it to the classical bits. It's performing the operation. And again, we're gonna simulate now using QxQ simulator, using the same instructions we had from when we generate the Bell state last week, the Bell states last week. It's gonna do 1,000 shots, 1,000 tries, and it's executing. Now, if you see when we shift enter this, whenever I do shift enter, I'm gonna have slightly different result here, close enough to 0.5, because it's a simulation of what a real quantum computer does. It's not anymore black and white result as the state vector does. It's doing a simulation of what a real quantum computer does. Okay, so now we're gonna play a bit more quantum. We're gonna do it better. Oh, in the homework, we're gonna go back to this. So I didn't forget, we're gonna go back to this question. I'm gonna show when I show in the homework questions, okay? I didn't forget. And as a last exercise to our homework, you're gonna see how to generate the phi minus Bell stage. And the phi minus Bell state is very, very similar to the phi plus Bell state, but instead of having, gonna write it out because I can't see it here. The phi plus Bell stage is given it's called phi plus because we have a plus sign here. The phi minus Bell stage, it's going to be very similar. It has a minus sign here. So to introduce this minus sign here, we need to do something, and there are two ways to introduce the minus sign here. One way to do that is applying the Hadamard gauge to a state that's one, a vector 1, and doing the same as we did for the phi plus stage, but instead of starting with 0, we're going to start as 1. Okay. Another way we have to generate this stage is adding a Z gauge, after the Hadamard gauge. This also introduces the minus sign, and I'm going to show you mathematically how. Okay, so the Hadamard matrix is given by, okay, the Z matrix is given by, so what I'm going to do the Hadamard gauge in the 1 vector first and show how I introduce the minus sign. The vector 1 is given by 0, 1. Okay. So as a result, I have 1 times 0, 0, 1 times 0, 0, plus 1 times 1, 1. 1 times 0, 0, plus minus 1 times 1, minus 1. This is the same as writing that's the same as writing so that's how I introduce the minus sign to my operation. Then when I apply the C0 gauge, I'm gonna do the GX here again, MUTC, just to show. When I apply my Hadamard gauge to my vector 1, because that's how I generate a vector 1, I introduce a minus sign here in such a way that when I entangle the states with the C0 gauge, I will have a minus signal. When I apply the C naught, I'm gonna have, after applying C naught, I'm gonna have okay, this is the final state we're gonna have. But as I said, we can also use a Z gate. That's another way to perform the operation. Oops. Yeah, the Z gate here. I'm gonna show you guys again how I do that. I know already when I apply a Hadamard gate that the vector, okay, I'm gonna do it again, it's better. I'm gonna apply a Hadamard gate to the 0 state first because it's easier to understand. And then you guys gonna have it free of doubt. Just perform the operation again. 1 times 1, 1 plus 1 times 0, 0. 1 times 1, 1 plus minus 1 times 0, 1. So this is the same as doing. That's the same as okay. So now what I'm gonna do, I'm gonna get this vector and apply a Z matrix to it. Okay. So I'm gonna apply, that's the same as doing this. Okay, that's the same as applying the Z. That's the same as doing, as I defined the Z matrix before. Oops, 0 here. 1, 1, and I'm gonna write the constant here, just to make it easier for me. What we have here. The result, I'm gonna have a vector that's gonna be 1 times 1, 1 plus 0 times 1. I'm gonna have 1, 0 times 1, 0, minus 1 times 1, minus 1. So as we know, this is, so I showed that there are 2 ways applying Hadamard gate to the 1 vector, or applying a Z matrix to after I apply the Hadamard gate, and that's what we have here. Okay, so cool. Now let's use QxQ simulator. So the simulator I'm using now, it's gonna be QxQ, so that's where we change in our function when we call it. We call it different, before we going state vector, now we're going QxQ. Define a job, I define the result, and I define the counts. And now the vector I want here is the phi minus that I already have here, the phi minus. And then when we press Shift Enter, whenever I press it, I have little noise that changes the result. And that's how the QxQ simulator works. Okay, so you guys try by yourselves. It's very simple if you do according to the homework last week. The Jupyter notebook last week has all these instructions. You can just copy and paste to this notebook and do it very easily. So now quickly we're going through the questions in Canvas, because there are some questions that's what you're gonna give you the grade. So, and make sure, of course, you learned. Into the dashboard here again, just to find the quiz. Quizzes. And then let's go to this week homework. Should be here. Yeah, so let's see. Solve the following tensor product by hand for the state psi, Which of the following represents the correct numpy state vector psi? That's great because that's exactly the first thing we did in our notebook here. This is the vector. And this is the vector, so easy. I'm gonna zoom it a bit more so you guys can see it better. Okay, so yeah, that's done in the Jupyter notebook. Okay, exactly same question 2 we did in the notebook. You just need to go back and see what was the result multiplying the matrix by our vector psi. It's exactly here. Okay, and that's how you define it. So far so good. And now using NumPy to solve psi, we need to write which vector we found. And then we go here, just do the operation, and we can see it here, the answer as well. So it's the same thing. And now question 4. Yeah, question 4, give the value of state phi. Yeah, but it asks you to tell the result of vector phi, but say psi here, but you should understand it's phi. But it's the exercise we did in the homework, on the Jupyter notebook here. It's the state phi. Yeah, it's phi, okay? So, yeah, now, yeah. So now, yeah, this is where we go back to that thing that I promised we would go back. That's what I was most concerned about. Let's read it very carefully. Trying to find my water here. Now the dog's barking. I guess I'm gonna put the dog in the call too. Gonna tell him to behave. So my dog's super cute. He deserved to be in the car. Just don't bring him here because he would do a big mess. But he's super cool.
Please show him next time.
Oh yeah, I will. If you guys hold on, when I finish, I can try to show him. I can try to call him. So let's hear. We have a starting state that's psi that's given by 0, 0, 1, 0, and a final state phi that's given by 0, 0, 1, 1. So we have a starting stage, but make sure I'm copying it right, psi, that's 0, 0, 1, 0. And I have a final state phi that's 0, 0, 1, 1. And from here, I'm already going to give a hint. So see that the only difference from the starting to the final is this one here. It means it was flipped. It was flipped from 0 to 1. And it smells like it was flipped because of this guy here. This smells like a C naught. Of course, there's a C naught here. So it tells us something. Let's try to draw our initial stage.
Why don't you just flip the last one, put
Yeah,
it-
I'm gonna show very slowly because this morning I did that to a student and he liked the explanation, so maybe it can help people. So I'm gonna show the equivalence, just like how I did to him. So let's see, this is the initial stage, and we know that's how this is displayed, okay? I'm just gonna try to make it smoother line here. So this is the initial stage. So what shows to us is that the last stage was flipped. And this state here is 1. So it seems like in the last state, in the final stage, something changed here. If it was flipped, it was probably a C naught. If this was 1, it's probably this guy commanding here. So that's how you're investigating, you know that in the end, this is the circuit you had. So why this was presented before? When you have 2 identities and one C naught, it just means where and when you're gonna apply your operation. You have identity, identity, and then C naught applied to the initial state that was 0, 0, 1, 0. It means that in the sequence, you have a C naught applied to this, an identity applied to this, and an identity applied to this. Sorry, my 1 disappeared when I draw the circle. That's what it means. That's why you have identities here showing before, because if I don't have identities here, I don't know where I'm applying. If I don't have the identities here, I don't know where I'm applying the C naught. I'm gonna do it in red because I was using my hand. So if I don't have the identities here, I have just a C naught applied and I don't know where. But when I apply the identity matrices here before, I know when I should apply a C naught. It's gonna be the third operation that I'm applying. The third operation, bottom up, is a C naught gauge. So that's why you need the identity matrices here. But we also know that I can call this entire thing U. I can just perform math on the matrices and find that giant matrix we found before in the notebook. And that's what this matrix means. This matrix I tensor C naught. And that's why, so I hope I answered the question for someone who was curious before. That's how you use it. So yeah, now I guess I can answer some questions because we did the entire homework, I believe. Yes, we did. So any questions? No questions, I believe. So yeah, I will see if the dog is around because I promised. Let me see if he's around. Stormy, amor, can you bring Stormy?
Gisele, what's his name?
Storm, we call him Stormy, but he's Storm.
I thought you said Sunny, which is my dog's name.
Oh, no, it's the opposite of Sunny, it's a Storm.
Yeah.
Yeah, he's about to come. He's coming up the stairs now.
Here, this is my dog. Well, I don't know if you can see him.
Oh, so cute. Oh my gosh. Oh, I love doggos. Hello, buddy. There he is. With his one of his favorite toys. Come on, come on. You like to be baby.
Oh my goodness.
Wave to people. This is Stormy. He's the quantum dog. He's my part-time dog because He comes whenever the kids are around, so he comes. I'm gonna release him from his misery. You go, buddy. Here's your banana. Your banana. Yeah, we give him tropical toys because I'm Brazilian, so we give him toucans and like bananas and tropical toys.
Seems like he loves them. He was not going to let go of that banana.
Oh yeah, he fights. Now he run away because he doesn't want me to. But he loves to destroy them too. So yeah, I hope I helped you guys today. And yeah, now Storm is a famous dog. Everything he wanted to be famous because he loves attention.
Next week we need a picture of Stormy. Your artistic interpretation.
Oh, I will. Okay, cool. I'll do him.
Can I still ask some questions here?
Of course.
Yeah, so what's the purpose of this eye cancer product eye in front of the CNOT? Why don't you just write a CNOT directly?
Because the C naught in this case, if I just apply a C naught, I don't know where I'm applying it because a C naught, oops, yeah, a C naught just randomly put here could mean I'm applying it to whichever vector I have here. So when I write this identity matrix here before, I'm placing the C naught where it should be. Let's suppose I want the C naught to be here. I would need to write it here instead of identity. I would put a C naught here. And I would put another identity here. It's just for placement. It's a smart way to place your operator.
Okay, got it. Thank you. And but why you so it should corresponding to the number of qubits you have. Like here you have like a 3 plates,
Yeah.
but you have 4 qubits.
Yeah, it's because the C naught acts in two qubits at once. That's why. A C naught acts in 2 qubits at once. It doesn't act only in 1 qubit. So if I wanted only an X gate there, because the C naught is an X gate conditional, okay? If I want only an X gate, I would do, if it wasn't conditional, I would do, and then I would put an X here. If it wasn't a conditional, I would do this. But
Right.
I don't simply want to flip the last one. I want to flip the last one on the condition this one is 1. So a C naught acts in 2 qubits at the same time because it's a conditional. Okay.
So another solution for this question is really just to put a X gate on the fourth qubit, right? The
Yeah.
Q0 and put a X on it.
Yeah, it would be. Another solution for this would be just like adding, forget the condition. I'm going to use another color here. You would forget the condition and just add X here.
Thank you.
You're welcome.
Thank you, Giselle. I just want to say thank you for your explanations and your time.
Welcome. And it's my pleasure. It's been super cool to receive feedback from you guys.
Thank you very much, Giselle.
Thank
you very much.
Thank you. You're amazing.
Are you in Brazil or in America?
I'm in America because I live in New Hampshire now, but I'm originally from Brazil. Yeah.
Oh, wonderful. I know a lot of my colleagues from Brazil, and New Hampshire is a nice place, little cold.
New Hampshire is very cool. I have my warm vest on the entire time here because I'm always so cold in this house. And I'm not gonna lie, the temperature here is 70, but I'm used to temperatures around 80s in Brazil during this time of the year. So it's just to remind me I'm tropical.
I'm in Florida. I'm spoiled. You know, we have nice weather, but still. Can I ask you one more question?
Yeah.
2 questions actually. Last 2 weeks, unfortunately, I missed all your tutorials before, but for the last, this is the 3rd one I'm attending. Last week also you were there. I was told by you and somebody else in coding school that this is recorded. Your thing is on Canvas.
Yeah,
I
it
could not
is.
find it last week. Okay.
I'm gonna show you right now. You go to Canvas modules.
Okay.
You go to week 17 and 16, whichever week you like, and everything is here. To be fair, see, even week 13, it's still here. Homework section.
Okay. I see that. No problem.
You go to week
Second
16.
is, I know you are an expert in IBM and everything else you do in quantum
I'm not an
computing.
expert. I'm learning.
So how can you, what, I think there's one book reference you already give, Qiskit.reference book, right? For practicing all this.
It's literally called QxQ textbook. Let me see. QxQ.
There's
Yeah, if
also
you go to
the
the page here, you can find a textbook. It's learning QxQ.
There's also, Gisele, we have a list of resources posted on Canvas as well, like
True.
a reading list and resource list. So the QxQ textbook is included in that, and then some additional resources. They're not all about coding or QxQ, but plenty of additional material there.
Yeah, in Canvas now, you reminded me, I'm sorry, there is also a link to this textbook. It's super easy to find.
Okay, I see that. Thanks a lot. Maybe I'm asking the same question, but I just want to be sure I'm
It's
not
fine.
missing out something important, because you're an expert. I could struggle on the net for hours, not get the right stuff. You know?
I wish I was an expert. I wish I'm learning. Okay. We are learning always.
Are you applying to the AI or machine learning now?
So it's again?
Are you doing work in machine learning with Qiskit at all? And
No, not yet. No, I'm not. So I think now I should go because Rachel has her time too. And she needs to get to
Thank you very
close.
much. Have a good day. Have a good weekend, all of you. Okay.
You too, guys. Thank you very much. Have a
Thank
wonderful
you.
weekend.
Appreciate it.
Bye.
Thank you.
Take care.
Bye.
Have a
Thank you
great.
so much.
Thank
Bye.
you.
Good night.
Thanks,
Bye.
Gisele. I'll
Night.
post this
Goodbye.
recording on Canvas
Thank
here
you.
soon.
Bye bye. Have a
Thank you.
good weekend
Bye.
all.
I'm gonna
Bye.
leave.
Thank you.
Bye.
Thank you.
Thank you.